I am Lee Carlaw. I'm one of the forecasters of the Chicago Forecast Office here. Some of you, many of you, a lot of you may probably recognize this loop behind me. This is the Corn Belt derecho from back in 2020. Prolific tornado producer in our area, a huge wall of wind across central and eastern Iowa, 90, 110 mile per hour wind gusts out there, and transitioned into 15 line-embedded tornadoes in our forecast area. The reason I bring this one up is that tornadoes embedded within lines, you heard Walker mention this, quasi-linear convective systems, mesoscale convective systems, tend to be one of the more challenging severe weather phenomena to issue timely warnings for. And it's for a number of reasons. One of them is that they tend to be pretty rapidly evolving, on the order of seconds to minutes. Some faster low-level scanning strategies with the Doppler radar network have helped, but they haven't completely solved that problem. They also tend to form really, really close to the ground. Walker also talked about low-level vorticity and spin. We'll talk about that in just a little bit more. This is really just very difficult to detect. Supercell tornadoes, the rotation develops aloft in the mid-levels, so the chances of us seeing that are a lot higher. And related to this second point, the radar just might overshoot the low-level rotation entirely. We see that a lot with some of these lower-topped type events out here. So as I mentioned, some new radar scanning strategies have helped to some degree. Faster low-level scans, you've got more control over the radar, but we still can and do miss critical features between these radar scans. Phased array radar, this might be the next game changer. GOES 16 came out a couple years. That was a game changer for us for satellite. This might be the analogy for the radar network. One of our forecasters just got back from a test bed in Oklahoma. They were testing this exact technology and how it relates to improved warning decisions in the Weather Service. Some amazing stuff coming out of there. Unfortunately, though, these won't be installed until the 2040s at the earliest, so we will have to wait, but that is something to look forward to. So basically, until then, the question is, how do we better tilt and stack the odds in our favor on the warning desk to get ahead of these potential tornadic mesovortices embedded within lines? So we're going to focus specifically on quasi-linear convective system tornadoes in this talk here. So tornadogenesis 101, you saw a little bit of this with Mike and Walker's talks. So some of this will be a little bit of a repeat, but we're just going to aim to kind of reinforce these processes. You've all heard wind shear already. It's just a change of wind speed and or direction with height near the ground. And specifically, wind shear near the ground starts air spinning about a horizontal axis. So imagine this poorly drawn cartoon here. Out towards you is towards the east, and in towards the plane is off towards the north. So in this case, we've got a westerly wind blowing to the east that increases sharply as you move upstairs above the ground. And so if you imagine putting like a twig or something in this, kind of get the sense it would start to rotate like this, right? And so this is the curl right-hand rule from your high school or college physics course, right? So it sets the air spinning about this south to north oriented axis here, and the direction of spin is sort of indicated by these clockwise spinning orange circles there. This is called horizontal vorticity, and specifically environmental horizontal vorticity, vorticity caused by the environmental winds. So if you start plunking thunderstorm updrafts on top of these vortex lines, an interesting thing happens. If they're strong enough, they can sort of act like a vacuum cleaner, sort of sucking up these vortex tubes and tilting them into the vertical. You saw this in Walker's talk there. This is a famous diagram from J.B. Klemp's 1987 paper. It's a great nightly read as you're trying to get off, doze off to bed, right? It's a fantastic paper there on tornadogenesis and the dynamics of tornadoes. Highly recommend it. The additional aspect here too, this is mid-level rotation upstairs. The second step focuses on additional vorticity developing near the ground. This is probably one of the more critical aspects for tornadogenesis in lines. Temperature gradients tend to form additional sources of spin and vorticity in the atmosphere. These are typically along things like outflow boundaries and cold pools. We'll talk about that in a second. You additionally can form vorticity along synoptic fronts, cold and warm fronts. We're also used to seeing that along lake breezes. We're no strangers to those across northeast Illinois. This is a slightly different form of vorticity generation. It's called baroclinic vorticity generation. Vorticity or spin caused near thermal gradients in the atmosphere. So at your next cocktail party, that's probably the next big word you can throw out there that you learned here today. And finally, the longevity of any tornado threat ends up depending on the strength, or is modulated by the strength of low-level updrafts here. Will these updrafts be able to sustain themselves for a long enough time to increase the chances they produce a tornado, or will they get cut off by the cold air? So there's a balancing act between the strength of this low-level cold pool and the strength of the updrafts with the thunderstorms. So in these next couple slides, we're going to be taking sort of a, imagine you're looking kind of south to north, a side-on view through a QLCS or squall line moving from west-east or left to right on the screen here. Squall lines essentially are driven or modulated by their surface cold pool, and that cold pool is just a result of thunderstorm updrafts going up and then the rainy downdrafts coming down, cooling the air behind them and spreading out laterally in all directions. In the cold pool, unlike the environmental wind shear we showed earlier where the winds were stronger above our heads, typically the winds are actually strongest near the surface. The winds are accelerating as they're getting closer and closer to the ground. So if we do the same kind of thought experiment we did a couple slides ago, we're just inverting the sense of rotation in this case. So if you put like a big twig in this flow where the stronger flow is near the ground, it's going to start to rotate in this direction. So counterclockwise as we're looking on here. Strengths of thunderstorm updrafts on the leading edges of these cold pools then depend on the strength of the environmental low-level shear. So in this case, we've got three examples, a strong wind shear case and a weak wind shear case there on the right. And then here are the cold pools we literally just talked about with that rotation counterclockwise here. In the strong wind shear case, we're going to develop an opposite and opposing rotor spinning in a clockwise direction. And in the strong wind shear case, this rotor is going to be spinning really rapidly, pretty strong, right? In the weak wind shear case, it's going to be a weak rotor, and the moderate is kind of in the middle. If we start plunking thunderstorm updrafts in there, some interesting stuff starts to happen. In the strong wind shear case, because the environmental shear out ahead of the cold pool is so much stronger than the shear caused by the cold pool, thunderstorm updrafts tend to tilt away and down shear from the cold pool. So you kind of see that in this cartoon here. On the opposite end of the spectrum, where the environmental shear is really weak, you don't have a lot of wind shear in the atmosphere, but the cold pool is really strong, the cold pool tends to undercut these updrafts. They tend to slide up and rearward atop the cold dome. Typically don't see a lot of tornadogenesis in that case there. And the balanced one is kind of our Goldilocks syndrome there. We've roughly balanced the vorticity with the environmental wind shear with the vorticity caused by the surging outflow from the thunderstorms here. So the strongest updrafts occur when the circulations are balanced, and the weakest with cold pool dominant systems there on the right. For tornadogenesis, we're generally looking for these balanced states. What ends up happening is these updrafts end up lasting for the longest period of time. It just increases the chances that they could go on to produce embedded tornadoes. The shear dominant case as well, we tend to see these are actually very favorable for tornadoes because obviously the environmental wind shear is very strong down near the ground. These tend to be cases where we can actually get embedded supercell tornadoes that kind of get sucked up into these lines and merge with these QLCSs. We saw that actually a lot during the August 10th, 2020 derecho. There were several instances of that in our area. So we're basically looking in these left two panels, the balanced and the shear dominant regimes for favored pockets for tornadogenesis. So what does a balanced portion of a line look like if you're a radar meteorologist looking at radar imagery here? So this is an example on the right, and you might not be able to see the city names here, but basically from like Sheridan up through Naperville, you see how tight that reflectivity gradient is. We're going from clear air, no precipitation at all, to these deep reds, yellows, and oranges, really heavy precipitation, maybe a little bit of hail in there. It's a very tight reflectivity gradient in that region. Farther towards the north, across O'Hare and the northern portions of Chicago, you see how kind of smeared out everything is. This is the definition of a not tight, an untight reflectivity gradient, for a lack of a better word. In addition, in this region here, we identified that tight gradient. Look at how, this is a velocity product from the radar. This is sensing what the winds and the magnitude of the winds are sensed by the radar here. These blues and light greens are 50 to 70 mile per hour winds blowing just off the surface. And so look at how these strong winds are co-located kind of right up against, oops, I'm going to go back one here. So look at how those are right up against each other. That's a classic sign of a balanced portion of a squall line. In addition to, the radar obviously doesn't just scan at one level. That would be pretty pointless for us. It scans aloft. And so we've got multiple scans that go up and up and up in altitude here. And so that's what this little animation is showing you. We're tilting up and up and up with each of these slices. Notice in this balanced section that that gradient pretty much does not move. It's in the same place at every single tilt upwards with the radar. So that's another hallmark of these kind of balanced regimes in squall lines. So this section, again, near Naperville, Yorkville, is really balanced. This is probably the strongest portion of the line. This is cold pool dominant towards the north, where outflow has started to kind of surge out ahead and undercut these updrafts, and maybe another portion of a cold pool dominant area developing farther to the south. Another term I'm going to throw at you here, it's a lot of words, and it sounds more complicated than it really is. This is the updraft, downdraft convergence zone. You're going to hear me refer to this as the UDCZ through the rest of the talk. But this is a critically important feature when it comes to mesovortex genesis, tornado genesis in squall lines. All it is the demarcation between rain-cooled air, the cold pool we just talked about, and warm and moist and unstable air inflow feeding these updrafts. You can basically think of it as sort of the outflow boundary portion of the storm, but oftentimes this is tucked in to the actual updraft portion of the QLCS. So mesovortices, QLCS tornadoes, all that stuff tends to develop right along this UDCZ, remains tethered to it through its life cycle, and then eventually is either undercut or just dissipates. So the critical aspect here is the reflectivity gradient and its relationship to the location of the updraft, downdraft convergence zone helps us identify cold pool dominant, balanced, or shear dominant regimes within MCSs. And we'll show you a couple examples of that going forward here. So as a warning operator, kind of trying to anticipate pockets of enhanced potential for tornado genesis, the goal basically is to find balanced or slightly shear dominant sections of these squall lines where the chances for the low-level updrafts to sustain themselves and go on to produce tornadoes are the highest. So the most critical aspect, again, is looking for these balanced or slightly shear dominant portions of lines. We obviously need to have sufficient environmental low-level wind shear to keep these updrafts really strong and rotating and going for a long period of time. And then the last aspect, which I'll show you in just a second here, is the presence of a bow, a surge, or more especially a descending rear inflow jet into this apex portion of the line. This ends up converging low-level vorticity all in one spot. And I think you probably saw that ice skater animation in Walker's earlier talk. If that's ingested into an updraft, it gets stretched and we form a tornado. So where all three conditions overlap, conditions are favorable for severe weather and tornadoes embedded in squall lines. Unfortunately, not going to have a lot of time to talk about these additional features. Just know that internally in the Weather Service, when we're making the decision to issue or possibly more importantly and sometimes not issue tornado warnings, we don't want to false alarm a lot. There's all of these additional features we're looking at essentially every volume scan and especially every time we're making a warning decision. This last point here too, there's sort of this is somewhat important as well. The I don't like how that looks, right? That's comes with years of experience of looking at these things. There's sort of a gut check. And I found over my now 11-year career in the Weather Service that just gets increasingly more powerful. That's something to listen to as well, this innate sense that's built over time. But the main point of this slide, again, is to point out there's a lot of different aspects that go into the warning mode. We're not going to be talking about those too much today, but just realize that these are also important critical aspects. So putting this all together here, so we previously identified this balanced portion of a line here, a nice tight reflectivity gradient. I didn't show you this, but we've got strong environmental wind shear in this case. For those who are familiar with wind shear metrics, I think in this case the 0 to 2 kilometer shear was like 35 or 40 knots. Very, very strong for our part of the region here. We have a clear bowing segment as well. You see this kind of concavity that's developed, this backwards C look to the reflectivity field. And importantly, there's this area of reduced reflectivity developing across DeKalb and Kane counties. What's going on here is that a punch of air is coming in from the mid-levels. There's subsidence and drying going on there. So raindrops are evaporating, snowflakes are sublimating, and we're getting this notable drying portion out here. Possibly more apparent if we tilt up and look at velocity. These blues and now purples we're starting to see, these are 90 to 100 mile per hour winds that the radar is sampling. Not quite at the surface, we're 3,000 to 8,000 feet aloft, but look at what happens over, this is like a 10-minute or less radar scan, loop here, where this rear inflow jet is aloft and it's just increasingly descending and getting closer and closer to the ground and catching up to this tight reflectivity gradient at the surface there. In this case, things are evolving very quickly. Again, that radar loop was 10 minutes or less. All of these aspects are lining up. Severe, widespread, damaging winds are becoming probable in this area, and possibly embedded tornadoes. And so this would be one where we would highlight with severe thunderstorm and mixed mash of severe thunderstorm and tornado warnings. Some of you may already know what this case is, who are familiar with the radar imagery. This was the Naperville Woodridge EF3 from Father's Day of 2021. Again, a late evening one. This was just after 11 o'clock. There was actually another tornado in progress at roughly the same time just west of our office there in Plainfield. All right, so I basically threw, I don't know, that's probably 4 or 5 mesoscale meteorology seminars in 20 minutes there. So hopefully you got all that information and none of it's leaked out, right? So we're going to kind of combine all this and take a look at a case study. Don't worry, no tests after this or anything to let you guys out, but hopefully it'll be kind of a unique experience to sort of try to combine everything you've seen so far into an actual case. We'll work through 2 warning decision time steps here to tie this together. We're not going to have time to kind of dive into the mesoscale meteorology and the environment, unfortunately, but just know that the environment is primed and ready to go for severe weather here. Low-level wind shear is off the charts. Instability is sufficient for severe weather here. I will handle the first time step, and then we're going to look for a little audience participation in the second to see if we can sort of tie these aspects together here. Don't worry, it's not going to be too hard. All right, so here's our radar. Again, that's our office there in Romeoville, northern Will County. This is a radar loop. I think it's over the last 30 minutes or so. Reflectivity is on the left, and then base velocity, again, the kind of the winds that the radar is sensing, is on the right here. So let's let this play one more time to kind of show you how things are evolving. Our forecast area is basically right here. So this stuff is entering our area of responsibility. No severe reports yet. So just note the gradual, slow amalgamation here of these clusters of thunderstorms as they're entering into Lee and Ogle counties. Again, no severe reports have been received yet. All right, so if we think back to those ingredients we were talking about, the updraft, downdraft convergence zone is the critical aspect here. We're trying to diagnose every single radar scan. So we need to determine these MCS regimes, balanced and shear dominant areas. So again, the first step I'm going to do, I'm going to take a look and try to find this updraft, downdraft convergence zone. We generally use base velocity for this. We can use things like spectrum width and other dual polarization products as well, but this is more of a qualitative assessment. We're not trying to get things absolutely perfect here. And all this basically is trying to find where the character of the velocity wind field is changing from sort of this homogeneous looking mass out ahead of it, which is the free convective air, the warm sector, the warm moist inflow, and then where things change abruptly with strong winds coming in aloft associated with this MCS. And so if I were to draw a rough approximation of the UDCZ here, it'd be something like this. So you can see an abrupt character change in the velocity field in this case. I'll superimpose that on the reflectivity side again to show how the reflectivity gradients now interact in their relationship with this UDCZ. So the next step here is to sort of identify the regions using the reflectivity structures here to find balanced and shear dominant areas. So this first region I've highlighted from Sterling up through the Rockford Metro there. I'll go back. There's the UDCZ, and there's this line. Notice again how this reflectivity looks kind of, it's not tight, right? There's a lot of, for lack of a better word, there's sort of smearing going on down and away from this line that I've drawn. This is a hallmark of a slightly shear dominant portion of the line where the wind shear is sort of pushing thunderstorm updrafts a little bit down shear and away from the UDCZ. Farther to the south, southwestern Lee County there, Sterling in the Northern Bureau, look at the difference there in the leading edge of the reflectivity. That's a little bit tighter, right? We're going from these like kind of greens straight up to reds in basically no distance at all. Very tight gradient. We would classify this now as a balanced regime where everything is kind of right up against that UDCZ. So severe weather is going to be possible for both regimes with a focus primarily towards this area here in particular. So here's the radar loop to kind of put things in perspective with all the little cartoons that I've drawn on here. The second step now is to identify surges, bows, or rear inflow jets. And if these are starting to get close to the surface and impinging on this UDCZ, the red flags start going up on our head here. So what I've done is I've sort of outlined rough approximations of these rear or potential rear inflow jets. You see these enhancements in the velocity signatures. These, again, these light blues here in this case, about 60 to 70 knots, so 65 to 90 mile per hour winds just off the surface here. And again, I've superimposed those on the reflectivity slide there. I call these possible descending rear flow jets because they're still well aloft here. Our radar scan this far out, we're still at like 8,000 to 10,000 feet or so. So no indication right now that they're abruptly descending towards the ground, but certainly a concerning signal that I would want to pay close attention to going forward as a warning meteorologist here. There's also a little small bow and surge that's starting to develop in southwestern Lee County. You see again that concavity, that sort of backwards C shape there, hallmark signature of a developing surge. So in this case, so we've sort of started to satisfy the primary three ingredients that we've talked about earlier, the balance, the slightly shear dominant, strong environmental shear in place, and the presence of at least developing bows, surge, or rear inflow jets. The organization over just the last 15 minutes or so is also something to take into account and is slightly concerning because things are getting a little more organized. So in this case, we're probably headed towards our initial severe thunderstorm warning to cap off or start this severe weather event. Again, we're not going to talk a whole lot about these in depth. Unfortunately, just don't have enough time. But there are additional items that we're going to be looking at behind the scenes to sort of heighten our concern levels. The more of these that we start seeing and adding, and especially the longer lasting they are, the higher our concern gets. In this case, we don't really see any of these in this case here. This line is just getting going. It's in its nascent developing stages. We do have one nudger over here. We've got some low-level instability in place, but this alone would not be enough to tip the scales here to say, hey, I think it's time for a tornado warning. So in this case here, our assessment leads us to a base severe thunderstorm warning, strong to potentially damaging straight line winds are looking more probable here. And we might draw something that looks like this. I could spend a half day talking about polygonology as well. This is, if you hear any of the discussions internally when we're about to issue these, there's a lot of discussion that goes on about what is the best polygon to draw. There's a science aspect and there's also an art aspect to it. One of the big things here we want to keep in mind, we don't really want to make these too big. We don't want to make them too small. Things can leak out of boxes pretty easily. We also don't want to warn areas multiple times if we can avoid them too. So this box goes all the way to the edge of DeKalb County and then northeastern LaSalle there. Maybe this is a 75-minute warning. Typically, we'll do 45 or 60-minute warnings. The reason I choose a 75 here in this case is that these storm motions, this arrow here, is the expected location of this cell in the next 60 minutes. And I want to make sure that this line and the severe threat is out of DeKalb and LaSalle counties. So if I do a 60-minute, that's probably too short, cutting it too close. I don't want to issue small little slivers if I can avoid it. That just gets confusing. There's warning fatigue. There's a whole lot of issues with that. All right, time step 2. So we'll have a little bit of audience participation here to see if we can sort of address some of this stuff. Don't worry, it's not too crazy. We're moving ahead about 25 minutes after that first time step. So it's 10:40 p.m. I forgot to tell you that. It's in the evening here. So maybe another thing to keep in mind about how this is evolving. There's our severe thunderstorm warning. This is a 30-minute radar loop to show you kind of how things have evolved over the last half hour. So there are definitely some changes. Some of them are subtle. We'll talk through all of them here, though. Let's play one more time. It's a beautiful looking box, right? Looks great. All right. Got some reports. Numerous trees down in Stewart. No indication of what numerous means in the report, but we know that there is damage. Potentially could be pretty significant. And then trees and wires down there in the far southwestern corner. So we do have severe reports now starting to filter in. Okay, step one, right? So we're trying to find these balanced, shear dominant and cold pool dominant areas with a focus on the first two. So the first step there is we need to find this UDCZ, the updraft, downdraft convergence zone. So we're really looking for where in this area along the line is the velocity field changing abruptly. Where do you see a lot of gradients in the velocities? So if you can see some of these cities, are there any areas in particular you would say are close to that UDCZ? Maybe a little easier for people in the front. Rochelle, Stewart, definitely agree. How about farther southwest? Yep, absolutely. Yep, Princeton, Lamoille, Sublette, Stewart. Yeah, perfect. That's exactly it. I'd say you got 100% on that one. I would agree with that assessment. And again, we're just kind of qualitatively assessing. Remember, we're having to think about a host of different things. We're making a warning decision, and this process can only take a couple seconds to a few minutes, right? And so we're doing this repeatedly over and over again. So good job, though, I would agree. UDCZ there. So I'm going to copy and paste that on the reflectivity side there. So now, in this yellow shaded area, how would you classify this portion of the line? Shear dominant, balanced, or cold pool dominant? So what is the reflectivity gradient doing in relation to that line? Shear dominant, mostly shear dominant. I would agree there. I think that's a predominantly shear dominant area there. You see how we're sort of smearing these reflectivity, these 50, 55 dBz values kind of down shear and away from that line there. So yes, I'd absolutely agree. That's shear dominant there. How about this huge mess farther to the south? That's balanced. That's 100% balanced. Look at how tight that, and look at that. That's almost going from clear air or just very light precipitation right up to this incredibly sculpted reflectivity structure there. So gradients in the real world are usually not a good thing from a radar perspective. Bad things happen in close proximity to gradients. So balanced, very good, 100%. Big change in just 20 minutes. And in fact, this might not even be fully 20 minutes, maybe 15 or 17 or so. We went from kind of shear dominant to a small balanced area to almost balanced across this entire line now, very, very abruptly. We're going to identify surges, bows, and rear inflow jets here. And what I'll do, since there's a little more stuff going on, I'll kind of walk us through this one. They're all over the place, though, unfortunately, in this case. So we've got a rear inflow jet here. We've got a big one here near Stewart. Those purples there, that's 85, 90 knot inbound, so 100-ish miles per hour or so. Again, off the deck, 7,000 or 8,000 feet or so, but pretty substantial. So rear inflow jets. Down here in the reflectivity field, maybe a little hard to see with all the lines, but you see these tiny little backward Cs, 1, 2, 3, 4. These little nubs developing at the leading edge of that gradient. Those are small surges, small bows developing in the line. So that's a intense, I really wanted to highlight there, I guess, right, intense rear inflow jet right on the updraft, downdraft convergence zone. So in this case here, again, this is all happening really quickly. It's just only going to take a couple seconds for us. We need to figure out how many additional confidence builders do we have. So yeah, we definitely have this descending rear inflow jet, reflectivity drop. We've got enhanced bows and surges. Look at all these reflectivity nubs that we've started to develop. This strong, really tight mesovortex as well. It's tiny. You'd almost miss it if you were looking at things too quickly. But this little guy right along the line there at Northeastern Bureau there, just northeast of Lamoille, rotational velocity over about 30 knots out of that one. From a warning operator standpoint, that's fairly significant for line-embedded tornadoes. So that's also getting the red flags going up pretty quick in our head. So 25 to 30 knots or so. So in this case, we've got, not only are we satisfying the base ingredients over a large area of real estate, we're now also seeing at least 5 confidence builders and nudgers combined with an extremely rapid change in the character of this QLCS over the last 20 minutes or so. I think this would probably end up supporting tornado warnings from the warning desk. I'd be, if not, I'd be very concerned and critically watching the next radar scans in this case. So warning operator has trimmed our box on the west side, so we have a severe thunderstorm warning there. Something we might be able to do, and again, you give this option to 10 meteorologists, you're probably going to get slightly different answers to how the boxes are drawn. Maybe you know, some would maybe split this into 3. From just a simple perspective, 2 might work pretty well here, but tornado warnings are definitely warranted in this case. We want to take things towards the county lines again to avoid polygon overlap. People in multiple warnings at once gets really confusing. One warning is probably a little bit too big. There's just way too much real estate in here. That becomes a problem for NOAA Weather Radio. So a natural kind of geographic demarcation might be the LaSalle County line there in this case. The other aspect here from a warning operator perspective is that this line is now accelerating. We were moving at like 55 or 60 miles an hour on the last time step. We're now moving at over 70 in this case. So pretty soon, this line is going to be out of our original box. And so, hey, I need a downstream severe thunderstorm warning. We've had confirmed severe reports and damage out here. I see no reason why this isn't going to continue or possibly even get worse over the coming minutes. So here's the downstream tornado warning in effect there, including the Aurora Sugar Grove metro there. Does anyone know what this event is? See some people trying to figure it out. All right, before we get there, this is the next 20 minutes. So we just made that decision to issue tornado warnings. Stuff's gotten a little out of hand here. Again, 22 minutes, I'm sorry. So I think there was one pixel in here. We actually tagged nearly 110 knots there. At this distance from the radar, that's probably about 3,500 feet or so, but just a wall of wind in this case. So this QLCS continued to rapidly intensify over the next 15 minutes. I'll start highlighting, I think, some of the areas here. Weather Service survey, widespread 70-mile-per-hour destructive straight-line winds in this region here. This is an interesting aspect. I briefly mentioned this in one of the previous slides, this drying that's going on across central DeKalb County. Again, what's going on there, this is where the rear inflow jet is parked. It's up at initially 10 to 15,000 feet, and in this case, it's rapidly surging and punching towards the ground. As that's happening, air is warming, there's compression going on, so we're starting to dry out the environment. Rain, snow is evaporating, sublimating, and we're starting to lose the reflectivity in this case. And so that's what's going on. And then at the leading edge of that, you see, uh-oh, that's a big problem there, right? Well-defined nubs and paired front and rear inflow jets all over the place here. Scattered severe damage reports also continued a little bit farther south, but the main corridor of severe issues were up in this region here. All right. This was not a local case, so I was trying to trick you there a little bit. So I saw some people trying to figure out what this was. This actually was a nocturnal severe case from April of 2020 from the Tallahassee forecast area. This is southeast Alabama here. Unfortunately, the EOX radar there was struck by lightning on this last scan, so we lost all the radar data after it. But these signatures just continued. I want to say this actually continued all the way to the Atlantic Ocean into the early morning hours of the following day here. We zoom in on the radar site there. Just after or shortly after we issued these tornado warnings, there's an EF1 that develops, again, 4:20 Zulu, so what is that, like 11:20 Central Time, CDT? They're the Eastern time zone, I guess. Another EF1 farther to the south shortly thereafter, and then multiple additional tornadoes. There's actually an EF2 in there, and then as I mentioned, that National Weather Service storm survey, extensive corridor of widespread 70 plus. I think the office may have found some 90 plus mile per hour in there. So definitely a really significant severe weather event. That's all I've got for these slides. Hopefully this was like sort of kind of helped synthesize some of that information we talked about earlier. Again, I'll just wrap things up by saying that we still haven't figured out all the answers to how and why mesovortex genesis happens in lines of thunderstorms. Active research is ongoing there. I'm sure we're going to, over the next 1 to 2 decades, with the advent of radar, the radar improvements, I mentioned phased array radars, those are going to be a tremendous help in identifying these fast, quickly evolving scenarios. And research just continues to find new and exciting things about how these types of scenarios unfold and evolve, and we're being better equipped with more tools in our toolkit to better detect these and at least anticipate the potential for tornado genesis in the 10 to 20 minute time range here. So that's all I got. I'll stop yammering there, Paul. Thank you, guys.